So under Analytical Techniques, we're going to look at mass spectrometry and atomic absorption spectrometry. Please look in the corner up here for mass spectrometry because it was covered in the last video. We went through the details of how you excite materials and send them down here, and they get separated by mass. And so you can find out the relative abundance of the atomic masses here, and then you can find from the isotopes relative atomic mass. So there's a formula for that. Just went through some more questions that is not just for an understanding. So determine number of isotopes and their relative masses. So you have 1, 2, 3, 4, 5, 6, 7. They're the list here of those numbers. The highest one here is 98. And which ones are in equal amounts? Those two look to be equal. That doesn't. So I would say 97 and 94. And 100 over there. Okay. If you're going to work out the relative atomic mass and you've watched the last video, you'll have to get numbers from here. So say if that was that would have to be relatively low. Maybe 20 is probably too high because these might have to be 10. So maybe these are 5, maybe these are 10. And so you will get like 92 times it by 0.10, so that's 10%, and times this other one here by 0.05, 5%, and then add them all together and you'll get a final number. Okay, so go back to that video if you need to. So the second thing we're going to cover is atomic absorption spectrometry. And so to understand that, we have to do a little bit of background first. We have to understand how light is created. So light is created because electrons absorb energy in some form and go to a higher energy level. And then when they go back down to their normal state or another state, they release that energy in the form of a photon packet of energy, and the wavelength here, so this is a high wavelength, this is a lower wavelength, will determine what color it is. And so if you know from your electromagnetic spectrum, high wavelengths are gamma radiation, low wavelengths are like radio microwaves, and in the light spectrum, the higher wavelengths will be the blue, and the larger wavelengths will be the reds. So they're the colors we're going to see. And so this is how it was detected. So we either have, we have the substance here, it gets excited, and then we can see what wavelengths were absorbed, and that's called the absorption spectrum. And a very similar thing is the emission spectrum, where we put the detection somewhere else, and those wavelengths that get emitted are then detected over here. And so if wavelengths of light are traveling to the n equals 1 level, that will be ultraviolet. That's the Lyman series. If the wavelengths of light are moving back to the n equals 2 energy levels, that's the Balmer series, and that's light we can see with our eyes. You can see that the small movement gives a large wavelength, a large movement back gives far more energy, so there's shorter wavelengths, and so that gives us the blue region. Same with the ultraviolet, they're large movements. Small movements back to the n equals 3, that's the Paschen series, so that's infrared, that's heat, and that's lower energy. So you need to know UV to n equals 1, visible light to n equals 2, and infrared light to n equals 3. And so this is another big reason why we understand how electrons are arranged around atoms, because we can see exactly where they're going back to and where they've come from. And we can see that as the energy levels get further and further out, the distance between them gets smaller, because we can see that here. We can see that the distance gets smaller. Again, for moving back here, this is moving back to n equals 3, moving back to n equals 2, they get smaller and smaller, moving back to n equals 1, they get smaller and smaller, which means that they have, these ones on the outside have moved a smaller distance. And so if you've got this one here, this one is moving back this quite small distance. This is the smallest of all of them. That represents this line here. The largest one here is the Lyman here, moving all the way back from this 6th level down to the 1st level, and that will be this one over here. And you can see that's not too much difference from these three, and so you can see that these three are quite similar, but it is a fair bit distance from that one and that one represents that one over there. And so that's some pretty good proof. It's called convergence, that shows that the shells converge as they get further and further into higher energy levels, and that's shown here in the spectrum, specifically the hydrogen spectrum. Now this is a very good spectrometer because you can see the different individual lines. The one you do in the classroom probably won't be anywhere as near, and they'll all converge into one because your instrument's just not as sensitive. And so if your instrument's not as sensitive, you probably won't be able to see the convergence, and you'll just see individual lines just here, but they're actually more specific than that. And so we do know the actual values and the distances moved, and we can use various mathematics to work that out as well. And this is just a diagram showing you the convergence, which also shows you how we work out ionization energy from your periodic table. Basically, once you get to a point where you've excited the electron to such a point where it's come off, and there's no way for it to come back again, that means you've lost the electron. So that's the definition of the ionization energy. So that's how that works. Just a diagram of the absorption spectrum. You can see that these lines have been taken out because those particular energies are the energies that have been absorbed by the electron to move to a higher energy level. When they move back down, that'll now be the emission spectra. So you'll see that in the opposite of this. You'll see all the colors black here and these black lines as those particular colors that are missing. And so this is the emission spectrum. Your syllabus does talk about a flame test. So these are basically the colors that come off that you see. Obviously it's quite crude, such as copper is just a green color, but if you use an emission spectrum and use a prism, you can break up those greens and some other colors that were masked, and you get a very specific fingerprint. And so this is the sort of thing that you can see. Helium was discovered using this method because helium is quite abundant in the sun and not very abundant on Earth. And so you can use this not only just to fingerprint and tell exactly what elements you have, also the intensity of the colors can also give you, you can use a standard scale here of different concentrations of, say, sodium to work out what particular concentration of sodium you also have in your sample. So it's both qualitative and quantitative.